A warm good evening to one and all present here. Today is the fourth and final day of the 4-day online workshop on analysis techniques for material characterization. Let's start our meeting with a silent prayer. Okay, thank you. Instructions. All the participants are requested to turn off their mic and video so that uh, the data can be saved. And also, instruction 2, a feedback link will be provided to you via this Google Meet, YouTube, or in the WhatsApp group. All are requested to fill the feedback form. It will be treated as your attendance. As you all know, today is the fourth and final day of the 4-day online workshop on analysis techniques for material characterization. I welcome I use this opportunity to welcome our HOD, Dr. Smita Tangachan, who is the PA of this project too. Uh, I use this opportunity to welcome Dr. Sanu Matthew Simon, Assistant Professor, Department of Physics, who is the coordinator of this program. I also use this opportunity to welcome the participants who are the core people of this workshop. At last, but prominently, today we are eagerly waiting to listen Dr. Adon Jose, Assistant Professor in Contract, IIRBS MGU Kottayam. He'll be delivering a talk on the topic photoluminescence spectroscopy. Use this opportunity to welcome Dr. Adon Jose too. Now I invite Dr. Smita Tangachan, Head Department of Physics and the Principal Investigator of this TST Search project, to introduce the speaker. Over to you, ma'am.
Good evening, all. It's my great privilege to introduce today's resource person, Dr. Adon Jones. He is currently working as assistant professor at IIRBS MG University. He has completed his PhD from MG University on the topic luminescent characteristics of rare earth activated glasses. His area of research interest includes photoluminescence, photonic devices, rare earth activated PL materials, etc. He has around 26 journal papers and 3 book chapters to his credit. Also, he has edited a book. He is also working as reviewer of many high impact journals. So, on behalf of MA College and all participants, I invite Dr. Adon Jose to lead the session on photoluminescence spectroscopy. Over to you, sir.
Thank you, Dr. Smita, for the kind words about me. Also, a big thank you to all the organizations for inviting me to this session. Let's begin our presentation. Is the slide is visible?
Yes, sir, it's visible.
Okay. Good evening to all. Today, I would like to share some brief idea about photoluminescence spectroscopy. We knew that luminescence is one of the interesting topic that we have goes to in our daily life. It's an integral part in our lighting devices, mobiles, laptops, security applications, and we can see its applications even in our nature too. We all are really fascinated to watch the glittering stars, the beauty of fireflies, etc. So today, we are mainly focusing on how we analyze a luminescent material. So my presentation mainly focuses on these aspects of photoluminescence spectroscopy. So first of all, I will give a brief introduction about the luminescence. Luminescence is a broad term. Usually, we are used to describe the emission of light from a substance or a material that has absorbed energy. We can say that the electrons in atoms or molecules actually get excited to higher energy levels by various means, such as heat, or it may be through light, electricity, or many other chemical reactions, and then it will return to the original energy levels by releasing the excess energy in the form of visible or invisible light. I think this emitter light carries this material's signature, and based on the method of absorbing energy, there are several different types of luminescence mechanisms. Actually, maybe you may be familiar with all of these terms. There are bioluminescence, electroluminescence, chemiluminescence, radioluminescence, and photoluminescence too. So today we are mainly focused on this photoluminescence. Simply, we can say that photoluminescence means it absorbs photons and then re-radiates photons. That means the photoluminescence, we can say that it's a phenomena where a material absorbs photons, usually they're having a higher energy in the UV, this ultraviolet region, and then it emits light at usually longer wavelength region as a result. So mainly the photoluminescence is also classified into two, which is fluorescence and phosphorescence. You maybe knew that fluorescence, in simply we define like that, is a sudden emission, whereas phosphorescence means delayed emissions. We can say that in fluorescence, a material usually absorbs photons at a specific wavelength and almost immediately emits at a longer wavelength. So this is typically in the visible region, and emission, this fluorescence is observed only when the exciting light source shines on the radiators. Whenever we are removing this exciting light source, its fluorescence is also vanishes. Whereas phosphorescence, which is termed as delayed emission, usually shows a distinct delay between this photon absorption and light emission. That means, actually, when a material absorbs photons, the electrons are excited to the higher energy levels and can remain in this excited state for a longer duration before returning to their ground state and emitting light. So we can say that this radiator is able to emit after the excitation radiation is removed. The lifetime of this emission, actually, as in the case of fluorescence, we studied, it's about of the order of 10 raised to minus 8 to 10 raised to minus 4 seconds. Whereas as in the case of phosphorescence, this lifetime of these electrons which occupy in the excited state is of the order of, I think it's of 10 raised to minus 4 to 10 raised to minus 2 seconds. So actually, when we have come across the theory of this phosphorescence and fluorescence, how it observes, we can say that actually the electrons in a stable molecules, which is actually always existing pairs. That means in an unstable state, usually the electrons are in unpaired states. That means the electron possesses an intrinsic angular momentum known as spin, and a pair of electrons can exist in one of two total spin states, depending on the relative symmetry of the spins of the two electrons. So if the two spins are in an anti-symmetric configuration, the electron pair has a total spin of 0. That means we can say that which is in the singlet state, while if they are in asymmetric configuration, then the pair has a total spin of 1, which is commonly known as triplet state. So this is a representation of singlet state and triplet state. So when a photon actually is absorbed by a molecule, the one of the electrons get excited or promoted to the higher energy level, and the molecule is now, we can say it is in the excited state, and the ground state molecule is always, which is probably in the singlet state, and it will obey this conservation of the angular momentum, actually the photo excited state must be also be a single state. So only this the ground state is also in the single state, and the excited state is also in the single state. On that case, when this excited molecule gets decays, that means it emits light from by decaying to from the S1 to S0. Actually, we can say that the spin multiplicity is same, both are in single state. That means it will results to the fluorescence. That means on that case, we say that the emitted light actually it's a case of fluorescence. Whereas the other case, we define that the photoluminescence are classified into the phosphorescence and the second case is phosphorescence and the first case is fluorescence. So, as in the case of a phosphorescence material, actually the molecule may undergo intersystem crossing to the excited triplet state. So, usually this term, the intersystem crossing that I'm going to explain the next slide, actually, it typically occurs in molecules with a high degree of spin orbit coupling. That means the coupling of the orbital angular momentum and the spin angular momentum of the electron, which allows the conversion between this singlet and triplet state. That means it follows a transition from the intersystem crossing defines the transition from a singlet state to triplet state. Please be noted that in the first case, as in the case of a fluorescent material or fluorescence, the transition usually observes from the single state to single state, whereas in the case of phosphorescence, the transition is observed as in the case of in between this singlet to triplet state. So from the triplet state actually back to the S0 or singlet state by we already say we says that actually it's a forbidden transition because the spin multiplicities are different because one is in the triplet state and the other is in the singlet state. So even if the spin multiplicities are different, the spin orbit coupling actually relaxes this restriction and a radiative transition from actually the T1 to S1 becomes possible. So even if we can say that the spin orbit, if it is forbidden, even if it is forbidden, we can observe a transition from T1 to S0 by a much slower time scale. That means we can thus on that type of transition we generally observe phosphorescence. And also we can say that the color of light emitted by a fluorescence is nearly independent of the wavelength of the incident light. All of these phenomena can be actually we need to explain on the basis of Jablonski diagram, which is shown in this figure, which is the main working. We can explain the behaviors of all kind of luminescence behaviors based on this Jablonski diagram. That means based on this diagram, we can see that actually there are several relaxation processes exist in the luminescent material, photoluminescent material, which are non-radiative relaxation processes and radiative processes. Actually, the luminescence bands can be either fluorescence or phosphorescence, depending on the average lifetime of the excited state. We already defined that as in the case of fluorescence, it's of the order of 10 raised to minus 8 seconds, whereas in the case of phosphorescence material, it is of the order of around 10 raised to minus 4 to 10 raised to minus 2 seconds. So this based on this average lifetime of the excited states, actually the luminescence band, we define whether it is a fluorescence or the phosphorescence. So the relative broadness of the emission band actually is lighter to the relative difference in equilibrium distance. We can define like that. The relative difference in equilibrium distance between the excited emitting state and the ground electronic state. So the photoluminescence of a molecular species is different from emission from an atomic species. In the case of atomic emission, we can say that both the excitation and emission are at the resonance wavelength. That means both are same. The absorbed photon and the emitted photon is of the same. While when we are considering the excitation of a molecular species, actually, it results in an emission that has longer wavelength than an excitation wavelength. So we are going to discuss actually about the spin multiplicities, also the important factors on the differentiation between this phosphorescence and this fluorescence. We defined that there were several type of non-radiative relaxation process naturally occurring in a luminescent materials, which are vibrational relaxation, internal convection, inter-system crossing, and non-radiative de-excitation. The picture actually illustrates all of these processes in the diagram. You can see on the diagram, we can say that the vibrational relaxation usually indicates, it means it's a type of whenever the excitation usually this type of excitation usually occurs to higher vibrational level of the target excited state. So the excited molecules, we can say that normally relax rapidly to the lowest vibrational level of the excited electronic state. We can see that there is, upon excitation, the molecule get the electrons get excited to this state, and through vibrational relaxation, it reaches this S1 excited state. It indicates simply in the time of vibrational relaxation. It's also a non-radiative process, whereas the second case is internal conversion. As in the case of internal conversion, we can say that if the molecule is excited to a higher energy excited singlet state, that means than S1, that is from the S2 here, a rapid non-radiative relaxation usually occurs to the lowest energy singlet excited state. So this relaxation process between electronic states like spin multiplicity, that is S1 and S2, are called, usually refers as the term internal conversion. Whereas the other term, actually, the non-radiative, no, the other term is inter-system crossing that I already mentioned in the previous slide. Actually, it is like that. Here, the non-radiative relaxation processes can also occur between the excited states of different spin multiplicity. Here we can see that there is a transition from this S1 to the triplet excited state. Both of them have different multiplicity. One have a spin multiplicity of 0 or singlet state, where other have the spin multiplicity, it is of the triplet state. So which usually refers of the time of inter-system crossing. And the fourth non-radiative relaxation process that actually we can define is the non-radiative de-excitation. Actually, the non-radiative decay of excitation energy actually leads to the decay of excited molecule to the ground electronic state, which is usually called de-excitation. And the amount of energy actually released in this type of relaxation process is usually of the form of heat and is compared to be very small. Whereas the important case that we are mainly focusing is about the radiative processes, which are fluorescence and phosphorescence. Actually, we already said that the fluorescence is a sudden emission. Here, we can simply say that the electrons get excited from the singlet state to another singlet state S1 and get it decays to the same singlet state. That means there is same multiplicity actually occurs, whereas spin multiplicity, that means we can say that it's a spin allowed transition, whereas in the case of electronic transitions between the states of different spin multiplicity are usually spin forbidden, and which is termed on the basis of this phosphorescence. So let me brief out this idea about on the construction of the instrumentation part of this photoluminescence spectrophlorimeter. Actually, whenever we are observing a spectrophlorimeter, it contains several parts like a illuminative source is there. So The fluorescence of a sample actually is recorded and measured by an analytic device, which is usually called a spectrophotometer. So scanning of the excitation, emission, or both the wavelengths is done in order to record the fluorescence. Through these extra arrangements, we can easily investigate its luminescence abilities and also its signal deviation with respect to time or temperature, concentration, polarization, or other variables also. So these are the major parts that I already said. We have a source and two monochromatics, which are excitation and emission monochromatics, and a detector. And follows that, we have a slits are there, grating elements are there, shutters are there, there's a sample compartment also. So the source of illumination that we are generally using, maybe it's a laser source or it's maybe a xenon arc lamp. So the lamp's light actually, we can say that a quartz-based window actually is used to isolate this excitation monochromator that we can see here from the housing of lamp, because whenever you are using this xenon arc lamp, maybe heat vents out of the device and it shields this quartz-based window present in between this excitation monochromator and the source actually shields against this heat vent out of the device, and also it may lead to the failure of the lamp. So preventing that case, maybe a quartz, usually a quartz-based window is present in between this source and excitation monochromator. And we usually use two type of monochromatics. That means first one is an excitation monochromator, and the second one is an emission monochromator. So there are several reflective optics usually we are used to in order to keep a great resolution over this full range of spectrum, as well as to reduce certain spherical aberrations and rediffraction that may be possible whenever we are arranging this instrumentation part. So other than this, we have generally certain gratings in between in this along with this monochromatics actually. The reflection grating is considered to be a crucial part of a monochromator usually. So its purpose actually is to disperse the striking light. So, and the other part actually we are generally using is the slits. The slits means they are very flexible slits we are using and the entrance and exit ports of these two monochromatics in order to bandpass. The purpose of it is to bandpass off this incident light is determined by the slits width of this excitation monochromator, whereas fluorescence intensity signal that we can control by the emission monochromator slit. So whenever we are setting a slit to it, actually we are actually the trade-off its intensity of signal versus spectral resolution we can possibly early control like that. So whenever the light falls from the sample as well as the detector, whereas we are using the narrower slits, we can obtain a higher resolution luminescence spectrum whenever using a narrow slits. If you are using a slits is of greater width, there may be the solution of the spectrum is observed to be decreases. So the other part is of shutters. This shutters is usually used for the purpose to shield the sample from photo bleaching or photo degradation for a long exposure of light from this. And this is the sample compartment is also there. And also we are using two types of detectors. The first one is a signal detector, and the second one is a reference detector. The signal detector is mainly based on photon counting, which is maybe it is of a photon multiplier tube, whereas the reference detectors is its purpose to monitor monitor the source for correction of wavelength and the time dependent output of the lamp, we can say like that. So these are the major instrumentation part of a PL spectrophlorimeter. And this is the optical layout. We can say that this is the optical layout of the Horibo fluorolog 4, Fluoromax 4 spectrophlorimeter. The all parts actually I have explained in this diagram, which is the block diagram, and this is the actual structure or the optical layout of the spectrophlorimeter. It is the layout of Fluoromax, Horibo Fluoromax 4 spectrophlorimeter. All of the times that we have already discussed in the previous slide. So next, we are going to introduce about how this photoluminescence we are actually measuring. So in photoluminescence excitation measurements, actually the PL intensity is actually recorded as a function of excitation photon energy. So we can under certain condition, which is based on that, is a photoluminescence excitation spectra is found to be, for certain materials, it is found to be equivalent to the linear absorption spectra. And this results from an absorption spectrum is valuable, very much crucial in determining the excitation wavelength for the emission spectrum. And the data extracted from the emission spectrum is often the peak emission intensity of the material, which is used to compare its electronic properties. So now onwards, we are going to discuss what are the data, actually, what are the different types of data that we can interpret from a we can obtain from a spectrophlorometer. So we can obtain the luminescence spectrum. Then we can also get a data of the excitation spectroscopy. And some advanced spectrophlorometers have the time-resolved PLS spectroscopy, which usually measures the lifetime and the relaxation process of a luminescent material. And also some arrangement of, or the integrating sphere attachment attached with the spectrophlorometers can usually record the quantum efficiency of the luminescent material. So here starts with this PL excitation spectroscopy. Actually, the primary criteria for obtaining the correct luminescence spectra of a sample, or the actual luminescence spectra of the sample, is to record it with the proper excitation wavelength. That means if we want to record the luminescence, the absolute luminescence spectra of a material, the first factor that we need to know is the excitation wavelength. So this can only be identified from the excitation spectra. So for recording the luminescence spectra, we need the excitation spectra. So we knew that we have maybe studied in the previous classes about the absorption spectroscopy. There are certain similarities between this absorption spectra and excitation spectra. Usually, the absorption spectra is a general scanning, and it can be done over the range of around 300 to 2000 nanometer range. It depends on the device that you are using. Whereas, as in the case of an excitation spectrum, we can only be recorded with a fixed emission wavelength. That means the absorption spectra, we can simply record its absorbance by varying the electromagnetic radiation falling on the sample. Whereas, as in the case of excitation spectra, we need to record, whenever we need to record the excitation spectra, the first factor we need to know is the emission wavelength. So, based on that emission wavelength only, we can record the excitation spectra. So, the intensity of excitation bands, whenever we are recorded the excitation spectra, the intensity of excitation bands, which based on the intensity of excitation band, we can only identify on which excitation wavelength we can observe the luminescence behavior from a luminescent material. Actually, the excitation spectrum usually refers to the range of wavelengths of light that are absorbed by a substance, causing its electrons to transition from a lower energy state to a higher energy state. It is similar to an absorption spectrum obtained. We already discussed that. But the excitation spectrum is typically obtained by, it is recorded by scanning the excitation monochromator through different wavelengths while monitoring the emission at a fixed wavelength. In the slide, actually, I have provided two spectrums. The first one is an absorption spectrum, and the second one is an excitation spectrum. You can see that there are several absorbance bands that can see in the spectrum. The bands are lights at 324, 336, 349. There are several absorbance bands that occurs there. Whereas we are recording that whenever we are recorded the emission spectra of that particular material by monitoring its with a fixed emission wavelength, we have obtained mainly the 6 excitation bands. It is also found to be similar with the absorption spectra. On the absorption spectra, we have observed an absorbance band at 349, whereas we have observed an excitation band actually at the intense excitation band at 348. And also we have observed several excitation bands, which is also found to be in the absorbance band. But actually, the significant why we are saying if absorption spectra is already recorded, then what is the need of excitation spectra? Because only the excitation spectra we can see the actual excitation bands, because here its value is 349. But the excitation spectra is not a general scanning. We are providing a fixed emission wavelength, and based on only we have recorded its excitation wavelength over a region, and this excitation wavelength is found to be very much relevant if you are considering the material for a leasing action or leasing pump source, etc. So actually, the photoluminescence excitation spectroscopy is a useful method to investigate the electronic level structure of materials with a low absorption due to the superior signal to noise ratio of the method compared to absorption measurements. Actually, there are several materials, those having the absorption intensity. Whenever we are recording this absorption spectra, it is found to be very much less intense. We didn't see an absorbance bands actually for certain materials. But whenever we are recording its excitation spectrum, we can identify the actual excitation bands actually observing, usually showing in that particular material. So it is also an important factor for raw absorption materials. Actually, we are preferring this excitation spectrum for identifying the excitation bands. The excitation bands can only, the excitation wavelengths can only say which excitation wavelength is that we have to supply for observing an intense luminescence from a luminescent material. So the intensity of this excitation bands actually identifies from this excitation wavelength. If we are observing this slide, we can say that the intense excitation band slides at 348 nanometer. So if you record the emission spectrum by exciting this particular wavelength, we can observe the maximum luminescence from that particular material. The spectra gives the idea that these all 6 excitation wavelengths can give the luminescence spectrum from the material, but we can say that the intense luminescence observed only when the intense from the when we are pumping the material with this intense excitation band. So also we can say that from this spectra, this is like a crystalline material, and we can say that the absorption spectra like this, and whenever we are recording the emission spectra, we can see excitation spectra, we can see some additional excitation band. This is more specific. The excitation wavelength is a specific spectrum, we can say that. But the absorption spectrum usually is a general scanning method. Actually, from the photoluminescence excitation spectroscopy, the facts that we can interpret is that we can identify the excitation wavelength, which is the first case. It is very important because based on this excitation wavelength, only we can identify the pumping wavelength, and only based on that we can record the exact or the correct luminescence spectrum from the material. Whereas the other case, I already explained that there are certain materials having less absorption bands. We can see then that type of materials we usually use the PLE spectroscopy for identifying which energy that we have to supply for getting excited that particular material. And other case on this by excitation spectroscopy also we can identify the presence of energy transfer. Maybe if you are preparing a material with having several active ions, and there may be some mixing occurs between them, and also there is a possibility of energy transfer from one active ion to another active ion, and it will may give certain important luminescence features, interesting luminescence features, all of them that we can identify from the photoluminescence excitation spectroscopy. Whenever we are synthesizing a material with this active ions, several active ions are present, we can see the presence of additional excitation bands from the PLEX spectroscopy. So actually, I want to explain once more because please focus on this diagram. Actually, we have this is the excitation spectrum of a glassy system. Upon exciting the sound, the excitation spectrum is recorded with the by monitoring the emission wavelength. We have observed actually 6 excitation bands here. For a better clarification, I show you the emission spectra of that material. That means, let us say that actually this is the excitation spectrum. We can say that the bands are, the intense excitation band is observed at the 348 nanometer. The second intense excitation band is at 363, and the third one is of 385. And whenever we are exciting the sample with these excitation wavelength, that means at the 347, 363, and 385, we can see that this is the emission spectrum we have observed, and this is the actually the emission intensity variation with respect to the changing the excitation wavelength. The second figure, please observe on that. Whenever we are excited the sample with the 347 nanometer and recorded the emission spectra, actually we have observed the intense emission band actually on this indicates in the red line, whereas if we record it with the 363 nanometer, actually it is found to be less intense, and it is found to be, as in the case of 385 nanometer, it is found to be lesser than that also. So it is also pointed out to the fact that the importance of excitation spectroscopy, because based on the excitation spectroscopy only, we can identify on what excitation wavelength we can record the luminescence spectra, and on that particular wavelength actually gives the proper emission from the particular material. So next we are going to this PL spectroscopy, the photoluminescence spectroscopy. Actually, the emission spectroscopy, we can say the photoluminescence as an emission spectrum. An emission spectrum usually describes the range of wavelengths of light emitted by a substance after it has been excited. So in fluorescence spectroscopy, usually the excitation monochromator is set to a specific wavelength known to excite the sample that we have identified from the excitation spectrum, that is the excitation wavelength, and the emission monochromator is scanned through different wavelengths, which is the reverse process of as in the case of the photoluminescence excitation spectrum that we have recorded discussed in the previous slide. As in the case of emission spectrum, whenever we are recording the spectrum, the excitation monochromator is set to a specific wavelength, which is known as excitation wavelength. Based on that, we are exciting the samples, and light emitted were evaluated on the basis of emission monochromator, which it is scanned through different wavelengths. So We can explain this photoluminescence spectroscopy by using several steps. The first case is photoexcitation. We can say that the form of light emission spectroscopy in which light emission comes from a process called photoexcitation. That means we have to supply a excitation source. We have to supply a source of light to the particular material. On that manner, the ions, the electrons in the ground state absorbs its energy and gets to the excited state, which is referred to as the photoexcitation. As the light is direct on the sample that I already discussed, when the electrons, and then after the excitation, what happens? When the electron come down to the excited state, to their equilibrium state, that means whenever we are exciting the samples, we couldn't say which is directly goes to the metastable state. This from the Jablonski diagram itself, we have explained that whenever providing a sufficient energy, the ions get excited to. There are several excited states, maybe observed, maybe we can see in a luminescent material. It get excited to a particular energy level and get decays to their equilibrium states, and by through several relaxation processes. We have discussed about several non-radiative relaxation processes that is present in a luminescent material, which are vibrational relaxation is existing there. There is non-radiative de-excitation maybe existing there, or other internal conversion are there, in the system crossing are there. So based on these all vibrational or those non-radiative relaxations, the electrons get relaxes to the equilibrium state. Then after that, it will emit light. That means it goes the radiative transition to the lowest ground state, which is called to be relaxation. So exciting the sample at a fixed sample, which is fixed excitation wavelength, and we are measuring this corresponding emission from the sample with varying emission wavelength is the process actually we are going through whenever we are recording a photoluminescence spectrum. So whenever we are recording this luminescence spectra, actually there are two different types of processes we can consider. The first one is of down conversion, and the second one is up conversion. The pictures actually that I have shown some results from published in certain journals. We can say that in the first case, actually we can see that the excitation source, the excitation wavelength is of the order of 348 nanometer, and we can see the emission that we have recorded is in the range from 450 to 700 nanometer. That means we are provided a greater energy, and we have only observed lesser energy. That is usually the case. The types of luminescence we are commonly called as the down conversion. Whereas some interesting area, this is interesting area of photoluminescence research is up conversion techniques. Actually, there are certain materials which usually show this up conversion phenomenon. That means we are providing the lesser energy source or lesser energy light falling into a particular material, and we can observe greater energy than the excitation energy that we have provided. The last figure, please see on the last figure, we can say that actually on that particular case, the excitation wavelength that we have provided is around 980 nanometer, and the spectrum we have recorded in the range of 500 to 700 nanometer, and intense emission wavelength is observed is of the about it peaks at around 575 nanometer. That means comparatively greater energy. That means lesser energy is provided, greater energy of light we can capture from that particular material, and that type of process is called up conversion. That means lesser energy provided, greater energy get, and the reverse process is usually called as down conversion. Is all of these features actually depends on the material's behavior, whether how it reacts with the excitation source, and etc. So on this slide, actually, I'm focusing on what are the data that we can interpret from a photoluminescence spectrum. I cannot generally say because in when we are referring a spectroscopic technique, there are certain type of spectroscopic technique we can usually use an equation for identifying its certain characteristics. But as in the case of PL spectroscopy, it is to be noted that it is a wide material, have an applicability of in wide material. So it varies from the its interpretation actually varies from material to material. So we cannot say how to interpret luminescent material as in the case of a thin film is generally different as in the case of a quantum dots nanocrystalline materials, and it is found to be different from amorphous materials and material to material. Actually, the interpretation is also different. So generally, actually, we can say something like that. Usually, the PL spectroscopy or from the emission spectrum, we can identify the band gap from certain materials because we knew that the band gap is the energy difference between states in the conduction and valence band of the radiative transition semiconductors. The spectral distribution of a photoluminescence that we observe from a semiconductor, it's we can use that data for identifying the electronic band gap also. Then also it gives an idea to quantify the elemental composition of a compound semiconductor. I think the band gap determination is possible as in the case of quantum dots. We can see that there is on this slide I have provided the variation of cadmium selenide quantum dots. Actually, we can see that whenever the particular size of that particular material is increased, its emission, its luminescence that we have observed is also found to be varies. That means the size, whenever the size matters, size changes, the light emitter from the material changes. That means we can calculate its energy difference or band gap from these kinds of materials by simply using the equation. The energy gap can be equal to hc by lambda. We can identify the lambda as 520 nanometer on this time, and also on this time it is 620 nanometer. In each case, whenever the size is increased, we can say we can easily identify its band gap from the spectrum we have observed from the photoluminescence spectroscopy by simply substituting the lambda value on the E equal to h3 by lambda equation. So the other technique we can identify is of the impurity levels and defect detection. There are several semiconductors or materials having several defect levels, and from the PL spectra, actually, we can identify the presence of the specific defects. Let us take a look on this diagram. This is the zinc oxide. I think this is a zinc oxide thin film. And from the observing this PL spectrum, actually, we can see that there are certain peaks that are mapped in this spectrum. And here, this the defect centers that we can identify. Whenever we are observing this type, we can easily identify what is the energy or corresponding to that particular wavelength by using the equation h by lambda, and also which also refers to the presence of several interstitial defects actually present in that particular material. The other case also we can identify the time resolved photoluminescence spectroscopy that I am going to discuss in the upcoming slide, and also we can identify the certain composition or stress strain symmetry or fluid half maximum from the PL spectrum of a material. How it is possible? Because each material can have certain characteristics in its PL frequencies, and based on that, we can identify the material's composition. Whereas if we observing it's a frequency variation in PL peaks, we can identify the stress or strain state of that particular material. And also based on analyzing the polarization of PL peak, actually we can identify the symmetry or orientation of that particular material. And also this is to be important as in the case of a photoluminescence or luminescent researches, is about the width of the photoluminescence peak, because the width of the photoluminescence peak have a certain significances, because when we are observing, this is the it's a one of luminescence spectrum, and here we have marked the full width half maximum of that particular peak. Actually, it is forward half maximum. We can calculate it by taking the difference between the two extreme values of the wavelength at which the photoluminescence intensity is equal to half its maximum value. It is possible to determine actually the size distribution of certain samples by using by observing this full width half maximum of certain materials, because if we are considering the quantum dots, actually I think the full width half maximum is reported to be, if it is greater than 30, then it is defined that its system is found to be a polydispersed in nature and has a large size distribution. Whereas, so the quantum dots having the full width have maximum is lesser than 30 is usually preferable for certain practical applications. Whereas I already said that actually this full width half maximum or all the luminescence behavior of a material that can be interpreted, in its interpretation is different from material to material. If you are considering certain this erbium doped fiber amplifiers, which are commonly used in telecommunication applications, on that case, actually we are mainly the research is mainly focused on how to improve the full width half maximum value of a I-safe region, wavelength region peak observed on that particular fiber amplifiers. It's I think it's of the order of around 1.5 micrometer range. There we can observe a broad peak, as in the case of IIRBS doped fiber amplifiers. And based on the full width half maximum only, by improving its full width half maximum, actually the researchers can accommodate the different window regions on that particular materials, and it's found applications in telecommunication regions. So that's why I am saying that actually there are lots of applications that we are discussing on the basis of or the interpretation is usually differs from material to material. One material have for it to have maximum can be defined its shape or size. One the other material we can identify its maximum number of photons that can be emitted from that particular material, and its applicability in several lighting, racing, and telecommunication applications. So the last factor is also the intensity of photoluminescence peak actually gives the idea of amount of photons actually emitted from that particular material. Whenever we can see that on this diagram, we can see that there are two dominant peaks which is found to be observed around 570 and at around 480 nanometer. And this light, this emission band has certain significance, because one is from in the yellowish region and the other is from bluish regions, and the material which shows this bands, actually based on this actually we can construct materials having a white light emission, which is the applicability of that type of materials. Next, we are going on the time-resolved PL spectroscopy. It is also a very important spectroscopic technique that we can interpret, we can obtain data from a spectrophotometer. Actually, we already said that all of us are actually, whenever if you are working in a luminescence field, it is found very much significance on the lifetime of the material. That means how much time actually the material stays in the excited state have its significance. Based on only that, we can consider the material for racing applications or lighting applications. You know, actually, as in the case of racing, the population invasion is an important criteria. And all of the, whenever we are preparing the luminescence material, it is very much relevant to take its time resolved PL spectroscopy, and based on that only we can identify the lifetime of that sample. Actually, here we can obtain some decay curves, which represents the variation in luminescence intensity of a material with respect to time after exciting it with the electromagnetic radiation of a particular wavelength. So from the PL spectroscopy, time resolved PL spectroscopy, we can obtain the principal information about the lifetime of an excited state, which include the nature of the state and the local environment around the ion or a molecule. Because if the molecule of the system have exists several interactions, based on that, the decay curves also found to be different natures. So simply, a lifetime is of a material is defined like that. It's a time required for 1 by 8 of the excited state molecule to return to the ground state. This diagram actually shows the decay curve of a material which has shown a single exponential nature. That means I already said that we have obtaining the data as in the case of intensity versus time, and it usually refers the time required for the 1 by 8 of the excited state molecule to return to the ground state. So first of all, we will fit the data using the exponential function. Using that, we can record its several decay features. Actually, from the decay data that we have observed can obtain from the spectrophotometer. Using on that, we can fit the data by using the XPredict one case that we can available in the origin. Actually, if you are fitting the data using a single exponential curve, that means is the its equation is y equal to y0 into raised to minus t by lambda t by tau. On that case, if the fitting is correct, we can identify its lifetime as tau, and we can easily identify the lifetime of that particular material. In some materials, actually, the data cannot be get fitted with the a single exponential function. In that case, we have to consider the double exponential function, and based on that, we can identify the average lifetime of that material by using these equations. These times actually we can obtain from the constant, the fitting parameters that we can obtain after fitting from by using the double exponential function. And actually, on the figure, actually, I'm showing the nature of decay curves that we can observe of a material with the different concentrations or doping several material active ions in a particular material. We can say that on the first case, actually, it shows a single exponential nature fitting like that. And also, whenever we are adding certain other active ions, its decay nature is found to be varies, and which it shows on double exponential nature, and it also shows a non-exponential nature whenever we are observing this type of nature too. So based on this, actually, we can identify the material's lifetime values, and it is based on that only we can propose that material for a luminescent applications. And the other thing, actually, is also a very, very important luminescent property that usually the quantum efficiency or the quantum yield. We are recording this quantum efficiency measurements using spectrophotometer by attaching the spectrophotometer with an integrating sphere attachment, which is shown in the slide. Actually, the quantum efficiency is the ratio of number of photons emitted to the number of photons absorbed. So through this technique, we are actually identifying this quantum efficiency. That means it gives the probability of excited state being deactivated by fluorescence rather than by other through the non-radiation mechanism, etc. So we can see that this is a quantum efficiency measurement of a sample. Here we can see that there are two items on there. The first one is of blank emission and sample emission, and the other case we can see then the blank excitation and the sample excitation. That means it indicates that first of all we are exciting the blank means a reference sample of the material that we are commonly using, and the sample is the actual sample that we need to know the quantum yield value, because only on the basis of quantum efficiency measurement we can say the material have the ability to emit light, because it is a ratio of photons absorbed and the photons emitted. So based on that only we can identify how much the material is have the potential to emit emit the photons on a certain regions. And for recording this quantum efficiency measurements, actually we need to know the excitation wavelength. You can see that it is very much similar the emission spectrum recorded as in the case of any material. So both of them, this PL spectrum is we can already seen from the quantum efficiency measurements too, but the instrument actually gives a comparison between the excitation and emission, and based on that only it is providing the calculating the quantum efficiency of that particular material. So the another thing that we need to focus that we are going to discuss is the colorimetric analysis. Actually, the colorimetric analysis maybe it is carried out by using the photoluminescence spectrum that we have recorded from the photoluminescence spectrophotometer actually. So what is the significance of this colorimetry that I am discussing here now? Whenever we are buying a lighting material like LEDs, we can see on the cover that certain color properties are mentioned there with respect to the light emitter from that LED. So if you are a researcher who are actively researching on the synthesis of a luminescent material, it is very much significant to identify the color properties. So if we prepared a material which can emit light, what are the peculiarities of that color, the peculiarities of that particular light emitter from that material is very much significant. So also we knew that the lights have an ability to control our mood too. So certain lamps will provide a relaxed atmosphere, whereas some of them have another mood. So the color characteristics of a material that we have prepared can be evaluated by using this colorimetry analysis. Actually, in the colorimetry analysis, which is based on CIE, that is the Commission Internationally Accurate System, is the most common method used to describe the composition of any color in terms of three primaries. That means red, green, blue. We can say what's the absolute emission, but absolute color of the material after exciting it with a certain excitation wavelength. So we are going to discuss, or we are interpreting the colorimetry analysis by calculating the CA color coordinates, which is termed to be x, y, and actually it will give the precise color measurements of that can be obtained from that luminescent material. Actually, the slide actually shows a CAE color chart of CAE 1931 standard, and we can calculate the color coordinates by using these equations. X, Y are usually the CAE X, Y sets are usually the color coordinates, and we can calculate the CAE color coordinates from using from the emission spectral data. We can record from the spectrophotometer, and also we can identify the color purity, correlated color temperature. All of these are certain color characteristics of a material. Usually the CAE color coordinates, based on that we can identify the correlated color temperature of that particular material by using McComb's approximation formula that I provided here. Usually we are defined like that. I already discussed the situation whenever we are buying a LED from the shop. Actually, we can see that from the cover that They are mentioning about a term CCT. CCT is the correlated color temperature. It gives the specification of the color appearance of the light emitted by a source related to the color of light with respect to a reference source when heated up to a specific temperature in degrees of Kelvin. Actually, the CCT value for household is usually found of the range of 3000 to 7800 Kelvin. For CCTs lesser than 4000 Kelvin, usually preferred for indoor lighting applications, and CCTs greater than 4000 Kelvin is usually reserved for outdoor lighting applications. There are certain theoretical point of view to calculate these CIE color coordinates, but nowadays it is found to be very much easy because in the net we can identify, you can use a CA color calculator material software available in the net. This is the screenshot of that page of a CA color calculator of Osram, and we can easily calculate this XY code CA color coordinates and its correlated color temperature values by simply substituting our spectroscopic data, the PL data on this here, and the software itself can easily calculate the CA color coordinate corresponding to the luminescence shown by that particular luminescent material. The data that I have input here is shown, and the software calculator its CA color coordinate as or that falls on this region, and it is marked as a blank spot in the CA color chart. And we can see here its CA color coordinates X, Y values. It is found to be 0.35 and 0.39. And based on that, substituting these equations, we can easily identify the correlated color temperature value of that particular material. That is found to be 408, 4846, and it is also shown in this software itself. So using that, we can easily calculate the color properties of the material that we have synthesized. So let's brief out what are the advantages and disadvantages of this particular field spectroscopy. Actually, the advantages are which is found to be sensitive and selective detection method. It's a non-destructive and having a wide material applicability and have a quantitative analysis. It can show high resolution spectrums and also have provided time resolved analysis and quantum efficiency measurements. That means if we prepare a luminescent material, we can get a complete idea of that luminescence behavior by using this spectroscopic technique. But the major disadvantages of this field spectroscopy that we are usually facing is about the several optical centers that might possess numerous excited states that are vacant at low temperature. It is found to be difficult, and limited depth of profiling. That means the photoluminescence spectroscopy primarily provides information from the surface of the sample, so limiting its ability to probe the internal structure or properties of thick or opaque materials. The other major disadvantages is the influence of external factors. Actually, the environmental factors such as temperature or humidity and ambient light can influence the PL measurements. So it is to be careful to control during experiments. And the other factor is potential photo bleaching. That means some materials are prone to photo bleaching. That means the prolonged exposure to light actually during measurements can alter the luminescent properties of the sample, which may affect the accuracy of the results. So that's it. Thank you.
Now, the session is open for doubts from the participants. Participants can either raise their hand or put their questions in the chat box.
Bebeto, I have read your doubt. Actually, the fluorescence quantum efficiency, the measurement from the spectrophotometer itself, using that spectrophotometer also, we can easily, there is a software actually in that particular spectrophotometer. Based on that, we can estimate or evaluate the internal quantum yield based on the spectrophotometer. Otherwise, we can directly calculate the quantum efficiency of a material, because quantum efficiency means it's a ratio of emitting the photons and absorbing the photons by simply taking the area of the emission spectra and the excitation spectra, excitation wavelength, the excitation bands area. By taking the ratio, we can easily identify the quantum efficiency value. But it's more preferable, I think, on the basis of this integrating sphere attachment, which is available in our School of Pure and Applied Physics, Mahatma Gandhi University. You can send the samples there, and they can easily directly measure the quantum yield of that particular sample.
Any other doubts? Participants, feel free to ask your doubts. Babito has asked another doubt. How does the PMT voltage affect the intensity of PL spectra? So please.
Okay, actually, the photomultiplied tube voltage. The factors affecting the PL intensity is mainly we can control it by only basing this slit. We can use the slit arrangements, and basically we can only control that much. We can control either if you are not getting a spectra, we can adjust the slits, or we can simply using certain filters for obtaining a clear spectra. For obtaining a clear spectra, I think we cannot easily use this change the photomultiplier tube voltage by because it is also it's a part of the instrument too. Okay. The next
Now, one
question.
more doubt.
Yeah, it's about the 3D plot of PL spectra. 3D plot of PL spectra, based on that we can identify. Actually, I don't have an. I think I don't have a knowledge about the contour plot. Actually, I didn't do that 3D map and contour plot. Actually, I already said that. Actually, the luminescence its application is different from material to material. Actually, I don't have any knowledge in the contour plot. Actually, the 3D map that we can easily draw from the origin itself, but I don't know about the much about this contour plot. Okay, how will we know with respect to our sample will give a PL spectra? For identifying whether the material is a luminescent material, usually you can take the absorption spectra first. Based on the absorption spectra, we can, if we obtain certain absorption bands, you can take its PL spectra by directly the PL spectra by using the excitation wavelength as the intense absorption band, intense absorption peak. If in the absorption spectra, if you have get a peak at intense absorption peak at around 340 nanometer, just take it as the excitation wavelength and run this photoluminescence spectra. If we can observe that particular PL spectra bands there, then we can see from the spectrum itself whether it is photoluminescent or not. Is it possible to understand the binding mechanism of the fluorescent probe and light while using for sensing applications? To my knowledge, I think it's not possible. Maybe that I have to read more about this interaction between this fluorescent probe and a light. Okay. Let's see. If two emission lines are seen in one spectrum, means the material can emit light in two regions. So the net, what will be the net emitter energy that we can simply identify by using the CA colorimetry analysis. Actually, the CA colorimetry, I have already explained that we can identify the XY coordinates by taking this or PL spectra values and the spectral distribution values, and based on that, actually, we can identify the absolute color emitted from that material. If two emission lines are there, based on the color emitter from that particular material will be the mixing of the two colors.
Okay, so if there are no other doubts, any of the participants may share their experience on this 4-day workshop. Please voluntarily, 1 or 2% give us the feedback so that we can know where should we improve. Anyone, please? Any 1 or 2, please say a few words so that we can know how it felt to you. Okay, thank you, Babito. I think nobody else is about to say anything. So let's wind up the session. Such an event would not become complete without delivering a word of gratitude. I use this opportunity to say thanks to our principal, Dr. Manju Kurian, who was there in each step of this program supporting us. I also use this opportunity to thank HOD Physics Department, Dr. Smita Tangasan, who is the PA of this project too. It will be incomplete if I do not thank Dr. Sanumati Simon, Assistant Professor, Department of Physics, who helped me so much in arranging all these speakers. Then, most important word of gratitude have to be delivered to the speakers, especially today's speaker, Dr. Adon Jose, who was the first person. We were in contact with many people, and he was the first person who uh, said, "Okay, I'll do." He was the first person whom we fixed for this 4 day online workshop. Thank you, Dr. Adon Jose, also for the very informative session on photoluminescence spectroscopy led today. Then I would like to thank the non-teaching staff of Marathonesius College who helped me very much in the live streaming of this program. I also use this opportunity to express my gratitude to my colleagues, Richu Rajan, Research Scholar, Department of Physics, MA College, Kodamangalam, as well as Rosemary Baby, Research Scholar, Department of Physics, MA College, Kodamangalam. Most important person of this program are you, the audience. Your immense participation, as well as you were very prompt to the instruction, as well as you help us in the smooth conduct of the program. Thank you, each one of. Thank you, each one. Thank you, each one, for cooperating with us. The certificates of the program will be issued within a duration of 2 weeks or so. It will be sent to your email ID, which you have sent us while registering. If anyone has mistaken the email ID and if you didn't get your certificate by 2 weeks, you can contact the organizing team. So thank you all. Myself, Anju Ganesh, Research Scholar, Marathonesius College, Kodamangalam, signing off from the program by wishing you a great evening. Thank you. Thank you all.